We got 18 people, I guess. That's not horrible. So I really always appreciate that you're here. If you're here, I like it. Are there any questions from homework? I think, Ethan, you were looking for something.
Yes. On page 392 for the prep skill for lesson 3.8. Number 2. I didn't really.
All right, so let's see, 392. Oh, here we go. Dude, come here. Hold on. Okay, this is bad. Oh, here we go. Sorry. My Kindle app is messing me up here. Number 2?
Yes, sir.
Okay. All right. Hold on, everybody. Wow. What is happening right now? Can you guys see anything? What is happening? Everything is locked on my computer. Can you guys hear me?
Yeah, it just says by continue. Wait.
What does it say?
Nothing. It was saying something about the meeting being recorded on my computer for some reason. It never says that, but
This is weird, guys. I
it's just.
have a bad feeling I'm going to get disconnected or something. Here we go.
Oh.
Hold on. All right, hold on, guys. It's just, I'm so over technological issues. Oh my gosh. What does that mean? All right, sorry. I think I updated my Zoom, and there's all kinds of nifty new things that I have no idea what the hell they're supposed to do. All right. So let's see. Now, can you guys see the book?
Yes.
Thank the gods. All right. So number 2, draw the graph of this equation. That's what you're asking about? This one?
Yes.
Okay. Can somebody tell me, or Ethan, can you tell me, do you know what the slope is for that equation, for that line?
Is it -20?
Beautiful. Why do you say that? I mean, that's correct. Why do you say that?
Y equals mx plus b, and m is -20.
There you go. And what's the y-intercept?
Would it be 45?
All right, and I'm going to pick on you a little bit.
Okay, yeah, that's fine.
0, 45, right? It's got to be a point.
Oh, yes.
Okay, I like it. Not a big deal. So you got it. So let's do another example. We won't do that one. I'll do one like it. Hold on. Let me get everything set up here. So if we can do one like, oh shoot, I just realized that is truthful. All right, guys, hold on. I don't know. All right. I changed all my setup here, so everything's in the wrong place. All right, let's see. Okay, here we go. So let me do an example like this one. So if I gave you an equation, y equals 4x minus 3, right? What's the slope? Anybody? Crappity doodah, Jeff.
4.
4, yeah. And let me put it over 1. So if I ever have a whole number as a slope, I just put it over 1 automatically because I know slope is a ratio, right? Slope is rise over run. Okay, what's the y-intercept?
0, common -3.
Good. So how do I graph this now? I know where to start. Oh boy, this is fun. Let's see. All right, that's enough. Where do I start? What do I plot first to plot this line?
The 0.
How do you mean?
0, -3. Never mind.
Oh, this one, yeah. You plot the y-intercept. You have to plot a point that's on the line. And then how do I get to the next point? Somebody else.
We have to go to the right for.
No.
Oh, rise over. This is 4-1. This is the next one.
Up 4 over 1?
Up 4. 4 over 1. So up 4. 1, 2, 3, 4 over 1. Bam. Now, that's basically what you got to do with the, holy crap and a half. How the hell did you miss everything, Jeff? Who knows? All right. Oh, I gotta play with all this new shit that I have on this updated Zoom. All right. The problem with this one is it's going to be a little bit worse because the numbers are a little bigger, right? But you just got to pick a decent scale. I mean, the slope is 20, right? Negative 20 over 1. So you just got to be careful about the scale you pick. But I mean, you essentially just do exactly what we just did. Does that help at all?
It does a lot.
Okay.
But my question is, I was writing when you were, I guess, graphing the second point. How did you do that again?
Oh, yeah. So you got to have a point. It doesn't matter if it's white or you just need any point. And so we plotted that point. And then the slope is go up 4 over 1.
That sounds okay. That makes sense. I
And
guess.
real quick.
Yeah, I guess I
What-
just didn't understand it last night.
Real quick, what point is this?
1-1.
1, 1. And of course, how do I check if that's the right point? Well, if it's on the line, it should work in the equation, right? So 1 better equal 4 times 1 minus 3. Put a 1 in for each. Is that a true statement? Is 1 equal to 4 minus 3? Yes. So that's a way to check. When you graph a line and you get another point, you can plug it in the equation to see if it works. That's the connection between a graph and the equation it comes from. All the points the graph goes through must work in the equation.
Oh, okay.
Isn't that cool?
It is. Thank you.
You're welcome. So there's a direct connection between the visual and the equation. I love it. All right. Anything else come to anybody else's mind? Anything else come to anybody else's mind? I guess that makes sense. You guys doing okay out there? I keep asking that. It's because I can't see anybody. Yes.
I have one more.
Sure.
On 3-5, question number 4.
What page is that? Do you know?
353.
Thank you. Number 4. Oh yeah, this one, everybody's favorite. Everybody's favorite. What's your question?
I was confused through the whole. I only did like half the problem.
Okay, so we did a problem basically exactly like this. Now tell me this. One person is going 2 miles an hour, correct?
Right.
The other one's going 1.92 miles an hour.
Yes.
Together, how far are they gonna go?
Per hour?
No. Now, how fast? How far are they gonna go?
Maybe 392 miles.
No. You're still talking about speed. I'm talking about distance. How long is one of these loops?
Oh, is it 20?
20. So the distance that one of them goes plus the distance the other one goes has to be 20 total, correct?
Yes.
If one's going to go somewhere, this is a slower one, and the other one's going to go a little faster, so he's going to make it a little bit further than the other guy. Together, they have to go 20 miles, right? You still with me?
I am. I'm
So
checking.
if this guy is going 2 miles an hour, and you tell me how long are they traveling? How long are they going on this loop? How long are they traveling?
20 miles. But
Listen, not how far, how long
oh,
are they traveling? And let me help you out. Isn't that what they're asking me?
many hours.
That's what they're asking me, correct?
Correct.
So do we know?
Not yet.
Not yet. Beautiful. Or else why would they be asking me a question that they told me? So what do I need to use then in place of just a blank space for how many hours they each travel?
X.
X. I love it. So X is the number of hours traveled on this loop, right? You with me?
I'm checking.
I like it. So this person right here, right? If they go 2 miles an hour for X hours, how far did that person go? So if you're going 2 miles an hour for 3 hours, how far do you go?
6.
6 miles, correct? If you go 2 miles an hour for 20 hours, how far do you go?
40.
40 miles. So if you go 2 miles an hour for X hours, how far do you go?
2x.
Beautiful.
Oh,
See, so I really desperately want you guys to understand the process we go through to get an answer doesn't change just because one of the things is a variable, right? I always would do 2 mile an hour times the number of hours, right? That's what I would always do. So if it's X hours, why would I do something different? It's the same. I just 2 times the number of hours, 2x. All right, so can you do the same thing for the second person?
would it be 1.92x?
Yes. And basically I've done the problem for you because now you know this distance, this is how far this guy went, right?
Right.
2x, and this guy went 1.92x. And what are those two supposed to do?
Equal 20.
Yeah, when you add them together, you're done. You just throw it in the equation and you solve it.
No.
So this captures the overall idea. If I knew this guy's distance and I knew this guy's distance, they would add up to be 20. And then so I write a math expression for this guy's distance, a math expression for this guy's distance, and I throw it in. So a lot of you guys, and I don't blame you, you just don't trust that you do the same thing, even if you don't know what part of it is. Of course you do. So all algebra is saying is if this guy is going 2 miles an hour, how would I find how far he went no matter how much time he went for? I would double the amount of time, correct? Because he's going 2 miles every hour, so I double the number of hours. Algebra just says that's what his distance is no matter what the number of hours traveled. And the same thing for this person. I really want you guys to get that because I can tell in the homework, a lot of you guys just don't trust that this works, that this, of course it works. Okay. You wouldn't say, I would double everything. You wouldn't go, no, if it's an even number, I'm going to multiply it by 3. No, that doesn't make any sense. It doesn't matter. I don't know. All right. Maybe. You guys hate all this? You hate it? You're like, damn it, Jeff. Why'd you have to get word problems in our algebra class? Because that's the main point of algebra, is to do real world shit. All right. Now, I will tell you this. Are there any more questions about this problem? I didn't finish it out because, I didn't assign myself the homework. I assigned you guys the homework. But I basically did all of it for you already, with a little bit of help. Do you have any questions about this problem? I mean, it's not done. I really want you to understand it's not done. Okay.
Yeah, I don't think I have any further questions.
All right. It's always fine if you do. I'm not going to be upset that if somebody has a follow-up question or didn't understand something I said. Okay. I'm going to stop sharing and see what people do. All right. Anything else, guys? Because like Wafa asked earlier, we do have that quiz this week.
I also have a question for
Yes.
number 11 on the same unit.
All right, let's see. So if the store manager started with 20 pounds, how many pounds should be added to create a mix that sells for that, blah, 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 right? And this is the kind of problem, a lot of people kind of look at this problem and think, I should be able to just take the numbers and do something. No, they don't give you enough of the numbers. What is it that you have to give a variable name to? Whoa, somebody's chatting at me. Oh, no, Trisha, it's going to be the same as every quiz. It's the midterm and the final that we do over camera. Somebody help me out. What is it that needs a variable name because we don't know it? You're welcome. Anybody? What is it you don't know? What is it they're asking you for in this problem, number 11? What are
The
they asking?
standard mix.
What about it?
How many
How much
pounds?
we need to
How
be.
many pounds? So, what are you going to call pounds of standard mix? What are you going to call it? Because we don't know what it is.
X.
Let's call it X. That's crazy. You could call it P. You could call it S, unless you're me, where my S's look like my 5s. Anyway, you could call it happy face. You could call it box. You could call it whatever. So X is a standard thing that we use, but it could be any symbol to represent the thing I don't know. So because it's easier to work with an actual symbol than it is to work with a blank space. Now, so I've got 20 pounds. Oh shit, I forgot. Can somebody, maybe I can look up here. What are the prices again? Can you guys see this? Is this $1.25? Am I remembering this shit? Is this $1.25 and the other one's freaking 95 cents? Is that what that is?
Yes.
I'm actually upset at myself for remembering that. I don't know. All right. I don't know why. All right, sorry. How much money is this by itself?
Twenty times 1.25.
Is everybody with that? Doesn't that make sense? 20 pounds times $1.25 per pound. Let me put that in there. Is everybody cool with that? Of course you are. $1.25 per pound times 20 pounds. Total money for that. How much total money is this? Somebody else. How many pounds do I have? I have X pounds and it's 95 cents a pound. So how much does that cost total?
X times 0.95.
I like it. Now, so this is premium, this is standard. What about the final mix? Holy crap, Jeff. Can you just try a little harder? Jeff, just try a little bit harder. You can do it, buddy. Final. Okay, this is, okay, for you, that's amazing. Okay, final mix. How many pounds do I have of the final? Hello? How many pounds will I have at the end? Sorry?
Oh,
20.
never mind.
No.
Oh,
no.
wait, no, you'll have 20 times whatever.
So if I add 3 pounds of standard mix in with 20 pounds of premium mix, you're telling me I'm going to have 60 pounds?
No, I'm stupid. You're gonna add that.
I didn't mean that to sound so evil.
No,
I
it's
really
fine.
didn't.
I need it sometimes, so it's
No,
all
no,
right.
no, no, no. It's okay. And again, it's a question of, see what I just did? I just gave myself a number for this. And I've done that before in this class, and that's an excellent thing to do in general. If that was 3, what would I do to figure out how many pounds I have at the end? I would do 20 plus 3.
So
If
you
that
do
was 10, 20 plus 10. So how many pounds do I have at the end?
20 plus X.
Kick ass. And of course, what do they tell me they want the price to be for the final mix? They just tell it to me.
$1.
$1 per pound. I like it. So how much money will the final mix cost? What do? I always do pounds times price per pound, pounds times price per pound. So what's the final mix going to cost?
20 plus X times $1.
Times 1. There you go. Cool. So if I take, then what am I doing physically? And what am I doing with the premium mix and the standard mix? What am I doing physically with those? I'm trying to say, here I have some premium mix and here I have some standard mix. What am I doing with them?
Add
Mixing
it to
them.
each other. Mix it
Adding them together. So what am I going to do with the cost for the premium and the cost for the standard?
Add it together.
And then I'm supposed to get how much? That, right? The cost for one, I'm going to add it into the other one. So the cost for one plus the cost for the other one has to equal the final cost. Does that make sense? Some of you guys got lost in the details. I know. But what do I always do? Do I take pounds times price per pound? So that's how much this costs. And I'm going to add it to the standard mix, pounds times price per pound. So if I add these together, I should end up with how much money it would cost to buy the whole damn thing, shouldn't I? Doesn't that make sense? The amount of money for this plus the amount of money for that equals the amount of money for the whole thing. Yes, maybe, yes, no? You guys hate it? You guys hate it. All right, I understand. Let me see. So what if I had, it's $1.25 per pound, and I got 20 pounds. 95 cents per pound, and let's say I have 10 pounds, right? So I would end up with 30 pounds, and I don't know how much it would cost per pound, do I? No, I don't, right? And this is what the first problems, all right, stay with me, Nate. Yeah, guys. This is what the first few problems here asked you to do. It wanted to get you used to this idea. How much money is this? $1.25 per pound, 20 pounds. How much is that?
25.
25 bucks. Everybody with me? $1.25 per pound. How much does it take to buy 20 pounds? 25 bucks. How about this one? How much money does it take to buy 10 pounds if it's 95 cents a pound?
$9.50.
$9.50. I love it. So how much should the end result be total?
$34.50.
$34.50. Everybody with me? Doesn't that make sense? The cost for this thing plus the cost for this thing has to equal the cost after you mix them together. Doesn't that just make sense? No? Now, can somebody tell me the cost per pound for the final mix? What's the cost per pound? It's $34.50 for 30 pounds, right? So if you divide that, can somebody help me out? I should go in even. Let's see, 11.50? No, Jeff, try again. 11.50, dude. $1.15. It's all right. Anybody out there with me at all? Help me out? No?
It's $1.15.
Yes, right.
All right.
150.
Jeff, you can do it. So all they did on number 11, they told me what the final price per pound was going to be. They just didn't tell me this, right? So I didn't know this. So what do? I still do price per pound times pounds plus price per pound times pounds equals price per pound times pounds. That's exactly what this is down here. Price per pound times pounds plus price per pound times pounds equals price per pound times pounds. Yeah, I know. You guys. This kind of problem you can eat up. You can just attack this problem, correct? So watch this. All number 11 does is it says, all right, that's nice. That's all nice. But we're not going to tell you what this is. I don't know what that is. But I know that this has got to be $1 per pound. And of course, if I have 20 pounds and X pounds, I should end up with 20 plus X pounds. So multiply BAM plus multiply BAM equals multiply, oops, now that changes. Of course, all this changes. So then we get our equation down here. We get 0.95x equals 20 plus x times 1. That's exactly what we got down here. All right, that's enough of that one. That's enough of that one. The problem is you either believe you're supposed to be able to just take the numbers and do something with them directly, or you hope you can. No, you can't. You have to bring in algebra. You have to have a stand-in. I don't know what this is. Let me call it X so I can do shit with it. All right, all right. Anything else, guys? All good? Oops, shit. I'm gonna make you all sick. Let me stop doing that. Okay. All right, guys. If there's nothing else, I'm gonna get back into where we left off. Oh boy, Jeff, this is gonna take forever. Let me see. Bam, where am I? Oh, geez. Just trying to get around this book is crazy. So remember in 310, we did the systems of equations. Let's do this one here so we all kind of remember how this works. All right. This problem right here. So what kind of sucks about this problem if I want to use substitution? Because I really don't want to graph these things. That'd be kind of gross. So a problem like this. All right, now watch over here. Let me do an example. So if I have, I really don't even know if I'm talking to anybody right now because I can't see anybody. Let's say I have these equations here. All right. Right? This problem right here. Okay. Oh man, I could just be talking to myself. I have no idea.
We're here.
Oh, Patrick's here. All right. How do I proceed here? What do I do? Why is this problem not that hard? Which letter do you know something about?
X.
For sure. Yeah, you know something about X for sure. You know that X is 2y minus 1. Now, the more you understand what I just said, the more you understand algebra. Basically, a lot of you guys are going to say something which is true. I don't know shit about X. And I'm going to say, that's not right. That's not right. I know that X is twice y minus 1. So I do know something about X. It's sort of like saying, do you know how old that guy is? Well, I know he's twice as old as that other guy. So you don't know anything. No, I just told you. I know something. All right, I'll stop. Can I rewrite the first equation using what the second equation tells me?
Yes.
Yes, so I can take this.
4. Yeah.
Go ahead.
4. Multiply 2y negative 1 and plus y
Good.
equal 5.
Okay, so I said good because a lot of people forget this poor little guy. Now, why is the equation we just wrote better than either of these?
Just one more.
Yeah, there's just one letter. So I can solve for it, right? So I get 8y minus 4. Is that cool? Distribute. Plus y equals 5, 9y. Add the 4 over. Is this? I'm just going to kind of do this quickly, and I don't care. Blah, blah, blah. And you plug it back in to get what x is. Now, look at this problem over here. What's not quite right about this problem if I want to do it this way?
X isn't alone.
Okay.
If we wanted to solve for that.
And it doesn't have to be x, thank God.
Or neither, or none of the letters are alone.
I like it. We have no letters that are alone. Which letter in which equation is easier to get by itself?
Y minus 4x.
Yeah, yeah. So how can I get y by itself in equation B?
Plus 4x.
Plus 4x, kick-ass. So now it's exactly like this other problem we just did. Now I know something about y. So you guys finish this up. Now I know this. Can you use it? Go ahead. Same way we just did the other example over there. Oh, that would be a good idea. Oh yeah, that's right. All right. Well, this will be neat. Oh yeah, cool. I like it. All right. All right, guys. So if we rewrite A using B, this is 4x plus 3 times y. So that's all I'm doing. Here it says y there. All right, well, y is this. So I'm just going to put that in because that's what y is. And now that's a much better equation, right? So if I distribute, what do I get?
12x minus 18.
Kick ass. I'm going to add 18.
Combine the like terms.
Yeah, I like it. So x is
1.
1. And then you have to fight the urge to just move on because you're so used to getting x and being done.
You need to find y.
You need to find y. And over here, let me do this in a different color. Blood red. So over here, I know y is 4 times x minus 6, but of course x is 1. So therefore y is 4 minus 6, negative 2. So this is perfectly valid. If you stop right here and you circle your answers, you're good. What's a slightly better way to write the answer to this? Does anyone remember? Don't I know what both variables are, right? So I'm done, but what's a little bit better way to write the answer? Does anyone remember?
Oh, like that. Okay.
And a plot point, 1, -2.
Yes, because again, I could have graphed these, correct? And the answer would have been what? Would have been where? If I graph both those lines, where's the answer?
1, -2.
Well, no. All right.
The point 1 minus 2.
Yeah, the point where the two lines
Meet each other.
intersect, meet. I like it.
Mhm.
So that's why you can always answer a system of equations with a point, because that's what it means graphically. That's actually what it means. But so either way, you guys don't have to write a point. As long as you circle your variables, that's fantastic. But you could also write it as a point if you wanted to, because that's what's going on behind the scenes. Is this is where they would meet if you graph them. Is everybody okay out there? You guys okay? I like it how everybody's kind of taking turns turning your cameras on and off. That's kind of neat. All right. All right. I think compared to the word problems, this should be a little bit better. Oh, look, there's people. All right, let me stop. Let me clear all this away. Let's get back into chapter 4 a little bit. If there's no questions, no other questions here. By the way, I mean, there's a whole review section with answers at the end that you could do in preparation for that quiz, for example. So of course, the thing we did last time was we started talking about inductive deductive. I showed you how to analyze one of those dumb questions like pick a number, now double it, now subtract 7, now add your dog's age, now and the end is like the number of TVs in your room, holy shit, so it's just algebra. That's all it is. It's nothing magic. But there's some even cooler I don't care about the handshake problem. I don't care about it. Oh, all right, now look here. So a couple of definitions. So inductive reasoning is what I called inflation, right? So inductive reasoning is you see a few examples and you make a conclusion, right? So if I walk around and I watch people playing basketball and I say, I think that playing basketball makes you taller. I've used inductive reasoning. Is my reasoning correct? I mean, is the conclusion correct? Does playing basketball make you taller? No. Can you understand why somebody like an alien might believe that?
Yes.
Because a lot of tall people play basketball. Now, I played basketball, and I had a really good fadeaway shot because I am not tall, right? I am exactly average height, which meant, anyway, that's enough about me. But most people that play basketball are tall. So an alien could say, holy crap, if a human does this, they'll become tall. So that is inductive reasoning. So inductive reasoning is what is most often used, and it can very easily lead to the wrong conclusion. Are you guys with me so far? All right. Inductive reasoning is very easy to do. If the last 80 weekends has rained, wouldn't you say the next weekend is going to rain? I mean, wouldn't that be a normal idea?
Probably.
Yeah, I would say, yeah, I think so. That's inductive reasoning. I don't know what else. Anyway, so inductive reasoning is seeing a few examples. It's sort of like here's a classic example of inductive reasoning. You guys ready? You guys prepared? Can you tell me what the next number is in this sequence?
10.
How did you figure that out?
Because they just 1 plus 3 is gonna be 4, and 4 plus 3 is gonna be 7, and 7 plus 3 is 10.
All right. Is that necessarily correct?
Should be, yeah.
I'm trying to think of a different one. It's not necessarily correct. In fact, I've gotten in trouble. I can't think of one immediately, but this doesn't have to be the case. Let me see if I can come up with another one. Well, what if I said this? 2, 10, what's the next number?
18.
All right, I have one person says 18. Does anyone else say something different? Anybody?
Can be 50.
50. I love it.
I think that's it, right?
I mean, there actually could be more. I don't know. I'm not gonna.
Gosh.
Nothing's coming to mind. But does this example make sense to people? How did people get 18?
Add 8.
Add 8. How did people get 50?
Multiply.
Times 5.
Multiply by 5, right? Times 5 is 10, so times 5 is 50. I like it. So what about, let me get one more for you. You ready? You can do it, Jeff. Can you do it, Jeff? Maybe? Let's see. Wait. No, you can't do it. I don't know. I don't trust my brain this morning. There's other possibilities for that. So the thing I'm trying to get you to realize is making a conclusion based on specific examples could lead to an incorrect conclusion, but it's normally what humans have to do because that's all we got. And that's why we're often wrong as humans. So that's inductive reasoning. So is inductive reasoning difficult? No, not really. It's not difficult, but it leads to incorrect conclusions sometimes. So do you think that the process that proves something, that leads to a correct conclusion all the time, do you think that would be easy or difficult? If you had a process that could actually prove something and be correct all the time, do you think that would be easy or difficult?
That is easy.
Easy.
I love you guys so much. Of course, it's going to
Easy.
be more difficult because, all right, let me stop. Compared to this, it's going to be more difficult because that process would start with variables very often, would start with accounting for all the possibilities. All right, let me clear this away. All right, let's see. Let's get some other examples. So you can have, a conjecture. Have you guys heard of the word conjecture? It's sort of related to hypothesis. It's just, yeah, I mean, a layman's definition would be it's a guess based on observations you made, right? So just like we said, the conjecture was the next number is 10. If it's 147, my conjecture is the next number is 10, right? And that has a decent chance of being correct. A counterexample is like the 2, 10, 18, and I said it could be 50. Somebody else told me it could be 50. That's a kind of a counterexample to the conjecture that it's 18. So every time it rains, my softball game gets canceled. Our game was canceled last night. It must have rained last night is the conjecture. Can somebody come up with a different reason? What's a counterexample that would disprove this conjecture? I love all this.
COVID.
Oh yeah, there you go. Could have been canceled due to COVID. Maybe somebody on the team was tested positive, right? So they had to quarantine the whole team. You with me? So that's a beautiful current event. Anybody else got a different counterexample?
One of the sprinklers on the field burst and it flooded the field.
Flooded. Yeah, I love it. Field flooded. Fudge. Anybody else? Fudge. Anyway, we can keep going forever, right? I mean, you can come up with more and more and more reasons. So a counterexample shows how the conjecture could be false. Just like we did here, does the next number have to be 18? No, because it could be 50. So that's a counterexample to saying this is what's true. All right, let me clear this away. All right, here's something a little more mathematical. Look at this beautiful equation. Isn't that beautiful? Can somebody, you guys see this? Can somebody tell me if you put a -3 in for x, can somebody see really quickly that you don't have to do any work? Do you see what y is going to be?
It's gonna be 0 for first one.
Yeah, it's going to be 0, isn't it? If I put a -3 in here, isn't that 0? Does it matter what the other ones are?
No.
Because 0
Because all,
times anything
all gonna be 0.
0. All right, now what if you put a 7 in? Somebody else tells me. Puts the lotion on his. All right. Can you tell me what happens when you put a 7 in? What will
It's gonna
y?
be 10.
Stop.
For next.
No. Somebody else.
Okay.
I see what you're doing. But what's the whole answer going to be? What is the answer going to be if I put a 7 in for x? Come on, guys. What's the only piece of that matters if I put a 7 in? All right, I love you guys. So like you said, this will be 10, right? You guys with me?
Yes, I
What
said
will
10.
this be?
0.
0.
0. So it doesn't matter. So that's 0. So then my conjecture is, if you put any number in, you will get 0. So based on these two observations, based on those two observations, I can say, I think any number I put in there is going to be 0. Because I got 0 twice in a row. I mean, what the shit? It must be true that any number I put in there gets 0. Now, of course, can somebody see how that's not right? Can somebody give me a counter example? Can somebody show me how I don't always get 0? Just pick a number, put it in. See if you get 0. Don't use -3 or 7, obviously. Anybody? Can everybody just pick a number and put it in? So I'm going to pick 5. So y equals 5 plus 3 times 5 minus 7 times twice 5 minus 1. Is that going to be 0?
No.
I don't even care what the number is. I just know it's not 0. So that is a counter example to the conjecture. Don't let the words get in your way. I don't know if the words are getting in the way. That is an example that counters, that shows that the guess that was made is wrong. That's why we call it a counter example. I like it. Not marble. Marble is a type of counter. I'm sorry. That was a bad joke. All right. Let me, I don't care. I like it. I'm going to clear all this away. So counter examples are kind of nifty. They're pretty straightforward. Oh, how about this? I love it. Look at these yummy words, and they kind of define this one for you if you forgot.
I have a question.
Sorry?
I have a question. So
yes.
always counterexample is against of conjecture?
Yeah, the definition of counter example is an example that runs counter, that shows the conjecture is wrong. So runs counter to something means opposes that thing.
Okay, thank you.
Counter example by definition is an example that shows a guess is wrong. I like it. Is it true that every right triangle is isosceles triangle? What's a right triangle mean? Who remembers that? What's right triangle mean?
Has a 90
Has a
degree.
corner with 90 degrees.
Yeah, so there's 90, there's 90, there's 90. And isosceles means two sides have the same length. Does somebody else remember something about isosceles triangles, about their angles?
No.
If
I
this
didn't
side,
think they mattered, I guess they do.
if this side is the same length as that side, how do you think these angles relate?
They're the same.
Equal.
Yeah, so I always like to think of an angle being how wide something's opening its mouth. And then the side is the stick that I ram in there. I sort of think of the Rancor from Star Wars, but that's because I'm a geek. So here's the stick in the mouth of this thing, and here's the same size stick in the mouth of this thing. So these two mouths have to be open the same amount. These angles have to be the same. Oh, shit. Oh, we're getting serious now. Some geometry in your Monday morning. If this is 90, how big are each of these angles?
Both 90, 45, 45.
They both have to make 90, so they're both 45. I like it. Oh, I love you guys. Can you draw an isosceles triangle that does not have a right angle in it?
Yes.
All that has to be true, is that these two angles are the same, right? So I could, if this was like 30 degrees, can somebody figure out how big each of these would have to be? Ooh, this is a good little math problem. I love it. So if this is isosceles, thank God it's there, so remember how to spell it. If this is isosceles, you still didn't spell it right. That is an S. Okay, that's true. Can you figure out how big these two angles here are?
75.
There you go. I love it. 30 means that I have 150 degrees left. Cut it in half. 75, 75. Is that a right triangle? Is that
It
a
is
right
not.
triangle? It is not.
No,
It does
no.
not have a. So what's my counterexample? That is my counterexample. Right? Right? Number 6, you're full of shit, number 6. This is wrong. We found a counterexample. You guys, that's a pretty simple idea. If there's a guess that's been made, if I can say something that goes against what the guess says, that's a counterexample to that guess. All right, let me clear this. What if the
Would it really
conjecture? I'm
be
sorry,
a counterexample?
say again?
Because it says, would it really be a counterexample? Because it says that every right triangle is isosceles.
Oh shit, that's right. I was thinking about it the other way around. Does every right triangle have to be isosceles? So if I put a right, so let's make a correct one. That's wrong. So Trisha has pointed out I get minus 10 points for this. So if I have a right triangle, do both of these have to be the same size?
Yes.
All right, wait a minute. Come on now. If I have a right triangle, so let me make
No,
one.
right triangles don't have to be isosceles.
So this is a right triangle here. Forget this little piece. Are these angles the same size?
No.
Hell no.
No.
This might be 70 degrees and this is 20 degrees. So is that a isosceles triangle? No. All right, good. So the book is still full of shit, and so is Jeff, but we all knew that. All right. So every right triangle is isosceles. The counterexample has to have a right triangle that is not isosceles. So then you show that this person is wrong. All right, that's enough of triangles. Hold on. I'm going to clear all this away. You ready? Pop. All right, here we get some really cool shit. Sorry. I love these things. Triangular numbers are numbers that represent groupings of points that make triangles. Can you guys see how this works? Can you guys see a pattern going on here? Can you figure out what the next, so this is like a sequence, right? Can you figure out what the next one would be?
Yes.
What's the next one?
15.
Well, I got somebody saying 15. Does everybody agree? Anybody disagree? Does anyone take any stand at all on that?
I agree.
Agree? I like it. Agreeing is a good idea because what do they keep doing? Here they added 2. So then you can see this, the original one, and then they added 1, 2, 3. So they always add one more than they added before, right? So this was added 2, this was added 3, this was adding 4. So the next one should be adding 5 because you can see if I just continue 1. Oh, let's see if I can do this. 2, 3, 4. That's not bad, Jeff. 5. 1, 2, 3, 4, 5. Good job, Jeff. Look at you go. You're just amazing. All right. So then this should be 50. Is everybody understanding that?
Yep.
Okay. All right. Real quick. I don't know. Does this? Hold on. Let me clear this away. You ready? What would the next number be, of course? We got 1,
21.
3, 6,
21.
15, 21. I like it. I like it. I like it. Now, I don't care about their next question. Who gives a shit? Let me show you this. This is kind of cool. What pattern is this? Anybody? What's special? All right, there's 2 ways to look at that. Watch this. What do I add here?
3.
3.
What do I add here?
5.
5.
7.
9, 11, 13.
So what will the next number be?
15.
15.
So what's the next number?
17.
No. What's the next number? You told me what I add to find the next number. You haven't told me what the next number is yet.
64.
There we go. So this is the shit that's behind the scenes. This is behind the scenes. These won't ever show up in the sequence. Can somebody identify the sequence in a different way, please? What's special about these numbers? 4, 9, 16, 36, 25, hike.
They're odd numbers.
Wait, what?
Odd numbers?
Oh, no, because I got 36 in there and 16, right? Are you looking at these? These don't matter worth shit. These are how I got the numbers in the sequence. So whoever said that, you're right. I keep adding the next odd number to get the next number, but I'm talking about what the numbers in the sequence. The numbers in the sequence. What's the sequence? It's this.
They're perfect squares, right?
There it is. They're perfect squares. So now think about it for a second. Every perfect square is the next odd number away from the next perfect square. Isn't that kind of neat? Anybody? Isn't that a little bit neat? Every perfect square is separated by the next by an odd number, and the odd numbers go in order. Isn't that crazy? No, you guys don't like that shit at all?
It's a little weird.
It's a little weird. Now you ready for the next level? You ready for the next level? I don't think so. I'm gonna give it to you anyway. Here we go. You ready? All right. What is this the square of, for example? 49 is
7.
7 squared. What's this the square of?
8.
What's 7 plus 8?
15.
Freaking 15.
Oh my God.
What's this one? This is 5. This is 6. What's 5 plus 6? Freaking 11. So I'm not going to go all the way. I'm going to leave it out there for you guys. There's actually a neat trick you can use to calculate more and more squares of things. And that's all I'm going to say. But I just want to throw that out there. All right. I'm not going to take you the whole way. It's up to you if you want to think about it, but it's kind of neat. All right. This is one of the things I saw. I still remember the first time I ever saw this. I was like, holy shit, that is neat. That is really neat. All right. I'm going to clear all this away. Clear. Okay. Oh, now this one is way too cool. Sorry. I don't know if it's better to have a teacher that's like overexcited about everything or one that is not excited about anything. What the hell's the pattern here? I don't like the way they've done this. It looks a little weird. Let me kind of redo this. Maybe as I do this, you guys can see what the pattern is. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Can anyone see the pattern? 1, what would go here?
5.
Yes, 5.
9.
No.
10.
10.
10. 5. 1.
Okay. All right. And you can keep going forever, correct?
Yes.
Now, real quick. Now, stay with me. Stay with me. All right. This thing has a stupid, incredible number of uses. It's insane. Here's one of the most basic ones. Now, this is a little bit, I think this is fine. Can you guys do this real quick for me? Right? Just FOIL it out. Can you guys do that? Have we talked about that yet? Right? X times X is...
Yeah, is 2x.
No, come on. X times X.
X squared.
X squared. Oh.
X times 1. 1 times X. 1 times 1. X squared plus 2x plus 1. Can you just tell me in order what the coefficients are of what I got? What are the coefficients of what I got? Just tell me the coefficients.
The power of 2.
No, the coefficients.
Oh, that's the one below. X.
No, the coefficients. What number is in front of each one?
1, 2, and 1. Which, no.
So watch this. X plus 1 times X plus 1 times X plus 1 is X cubed plus 3X squared plus 3X plus 1. All All right, I like Trisha's face. That's cool. The face you're making, that's awesome. That is one little use of this weird thing that looks like somebody who's in prison who only has a piece of paper and a pencil and gets bored and starts writing numbers down. This thing, I can't even begin to describe to you. If you just look up Google Pascal's triangle, if you feel like it. We're not going to get too deep into it.
That's a little insane.
I agree. All right. Let me see, what time is it? I want to, all right, let's see where the book goes. We've already done number 10, basically. That's what I started. I'm going to erase all this. You guys ready? Pascal's triangle is awesome. All right. Oh, yeah, we already did all this shit. Let's see. Do they have anything else interesting? If not, I want to show you one more thing. Let's see. Oh, I don't care about shaking hands. I don't know why they're so interested in handshakes. Whatever. What is this shit? All right, that's bullshit. All right, let me show you something cool. Has anyone ever seen this? Sequence before? This is a weird sequence. It's really weird because it starts with 1 and then it's still 1. It's like, what the shit? Has anyone seen that before? Or can you see what the sequence is? There's a definite next number. Okay, nobody knows?
18.
No? What's 1 plus 1?
2.
2,
1 plus 2.
3,
It's 2 plus 3.
5,
3 plus 1.
8.
So what's the next number?
21.
21. Because that's 8 plus 13 is 21. No one's ever seen this before?
I've never seen this.
No? Okay.
I think I've seen it before.
Answer me this. Riddle me this. Notepads. You guys ever use note cards for notes and stuff? You guys ever use note cards for flashcards? Can you tell me a size of a note card?
3 by 5 cards.
3 by 5. What's another size of a note card? Don't they also come in 5 by 8? Right?
Yes.
Anyway, all right. This is called Fibonacci sequence. The Fibonacci sequence. Fibonacci, right? This sequence is insane. The sequence shows up in trees. If you count the number of limbs on a tree as it goes up, it'll be 1, and then 2, and then 3, and then it'll branch off and there'll be 5 and so forth. If it hasn't been cut for most trees, you're talking about anyway, I'm not, oh my God, you could have a whole semester talking about Fibonacci sequence. So if you Google Fibonacci, in fact, let's do this shit and then we'll call it a day. I'm sorry, I erased
Is that true what you were saying about trees?
Sorry? Here, I'll show you a nice visual.
Okay.
Hold on. Let me look
All right.
this up. If I can look it up on the internet, it'll be a lot nicer picture than anything I could try to draw. Fibonacci branches. Oh shit, this is gonna probably give me something really funky. Here we go, perfect. All right, now listen. This is not saying every tree, oh shit and a half. Where'd it go? Here it is. Why are you getting all this funky shit? No, I don't want all that. There we go. Here it is, all right. So this is real. This really tripped me out. Not every tree does this perfectly, but as you, oh gosh, as you go up, if I count the number of branches across, I don't know what these other numbers are. Just ignore these numbers. All right. So there's 1, and then there's 2, and then this one branches off, and there's 3, and then this continues, and these branch off, and there's 5, and it's difficult to find a tree that somebody hasn't pruned, right? But if you do find one, this is something that it actually follows pretty well. Not every tree does perfectly, and it has to be a tree that kind of grew up in no problems. Anyway, this is a bad example. Let me see. What if I do? Can somebody tell me anything you're interested in? U.S. Teacher Appreciation Week. I had no idea. I don't know. I don't feel appreciated. Fibonacci, give me something you're interested in. Anybody? Anything? Cooking? Music?
Crystals.
Crystals, dude. Let's see. I've not tried that before. Quasi crystals and the beauty of flower. Are you kidding me? Crystals of golden proportions. Oh, dude, this looks like some cool shit. Sorry. I kind of love the Fibonacci sequence. Anyway, it's too bad that we're not going to talk too much about it. In fact, I've talked more about it than we're really supposed to, I guess. But it's so insane. So you can see there's a lot of connections between crystals in Fibonacci sequence. What is a Fibonacci crystal? I don't like that stupid website. Blah 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 blah. Fibonacci. I said cooking. I don't think there's any connection between Fibonacci and cooking. Fibonacci series in cooking. No freaking way. Are you kidding me? Fibonacci pie. That's just some stupid bullshit. Anyway, I'm gonna stop. That's something you could explore on your own if you want to. It's another situation where it just seems like somebody was bored and they went 1 1's 2, 2 plus 1 is 3, 2 plus 3 is 5. I'm bored as shit. And it just kind of kept going, and it actually has applications. Does anyone use an alarm to wake up in the morning?
Yep, and it's very annoying.
What does it sound like?
It sounds like a baby jingle, like a
Oh.
baby toy.
Does anyone use one that goes something like that?
No
Close
way.
to that.
Close to that. All right. Is that pleasing to the ear?
No.
So most harmonies, most things that sound pleasing to the ear are a ratio of frequencies from the Fibonacci sequence itself. Things that are not pleasing to the ear are way off from ratios from the Fibonacci sequence. Fibonacci sequence, for some reason, has a direct connection between what humans find aesthetically pleasing and what we don't. It has application. So art and music, somehow stocks, but I'm not gonna. There's direct connections between Fibonacci sequence and what humans find aesthetically pleasing. It's kind of insane. So anyway, I talked more than I needed to about that. It's barely going to show up on anything that we do. It's just an interesting side note to look at. Okay, we ended up not doing a terrible large amount, but I think that's a good place to stop. Let me know if you need to hang out afterwards. Otherwise, you are free to leave and look up Pascal's triangle and Fibonacci sequence.
I already did. I'm gonna
cool.
look at that now once I log out.
Yeah, a friend of mine used
Thank you.
Fibonacci sequence with stocks, and he made money through the recession way back when. There's a nifty algorithm for using Fibonacci sequence and when to sell stocks and when to buy stocks. And I'm like, that must be nice to have enough money to do that shit. But, everybody good? What's going on?
All
Questions?
right, thank you. Bye.
Thank you.
Thank you so
both.
much. See you later.
Bye.
Have a good day.
You too.
Professor, I have a question, but it's not math related.
right.
Know that we have another midterm coming up.